Okay, how's it going, everybody? Hanging in there? Okay. No, I'm sorry. Okay. Is it this class that's causing the pain? Hopefully not. There have been some questions about grading on one of the assignments. Now, look, we're not going to make it like a doopy-doopy-doopy-doo everything. If there are issues, though, in general, send me a message in Canvas inbox along with the TAs. All right, so we have Min and I. So if you just go in Canvas inbox, you'll see that if you click on the teachers thing, it automatically includes them, or it puts them, populates it, probably with all three of us, in fact. So that's the preferred mechanism for resolving those types of issues. And if you send me an email, I'm trying to respond through Canvas. Okay, so it's better for all of us if we use the Canvas inbox. All right? I know it's not necessarily as nice, and it doesn't have all the features that our email has. It just keeps things separated. All right, and you can make sure that you're not going to get lost in the many other things that come to our email inboxes. Okay. In terms of the group projects, this is a blank slide at this point. Hopefully tomorrow I will have the revised pre-proposal assignment available on campus. That will be due on the 28th, so 2 weeks from tomorrow. So in the next couple of weeks, what we want everyone to do is to find two teammates, all right, and discuss some general ideas for what you think you might pursue. I will then spend some time going through and providing some feedback, even if you just have limited ideas, just to get us going and get us calibrated in terms of what I see is out there already with the literature or with examples and things, and maybe some points to think about. Maybe that your project is a little bit too aggressive for this semester. So what can we do to kind of make it something that you will not be upset with me about at the end of the semester? Okay. Or maybe it's like, oh, we should probably think about adding a little bit more detail. When you're thinking about your projects, it would be great if you also think about data that might be out there experimentally that you could use as your ground truth, okay, as you're thinking about, okay, does the simulation make sense? Any questions on the projects? We haven't, I understand, I would expect that you have some questions, because we haven't really outlined what we're looking for exactly. But do you have questions? Yes.
Can we not have more answers?
Yes. It really should involve ANSYS in some way, shape, or form, because we're going to spend most of the class using ANSYS. So you'll see in the survey, the questions are kind of going to be along the lines of, is it a particle dynamics question? In that case, you might think, okay, that MATLAB would be a good fit. Is it a solids question? Is it a fluids question? Is it a thermodynamics problem, heat transfer type of problem, which we're going to start covering today. So we'll ask for that, and then we're going to ask, is it going to be time dependent, or is it going to be like a steady state? And we'll get into a little bit more details on what that means. That should become clear kind of today, I think. And then we'll ask for your teammates, and then ask for a short description of what you're thinking about doing as a group, and then also a short description about what you individually will be contributing. So, should it use ANSYS? That was your question? Yes. I think when I taught last semester, there was maybe one group that decided they were just not going to use ANSYS. That I guess I don't want to single anyone out, but I think it would have benefited from looking at using some type of system that solves partial differential equations instead of sticking to ordinary differential equations. Console is available. If any of you are avid console users, that's another option. And there are many different tutorials in console that I've mentioned before that you might want to translate over to. Okay. Other questions? Should you use MATLAB for your final project? I would highly suggest that yes, for the plots and your paper. So if nothing else, MATLAB will be your plotting tool. It can do, of course, much more than that. Okay, any other questions? All right, well, here we go. Today, we're going to discuss flux in terms of what happens with a thermal system. We're going to talk about the heat equation. We're going to introduce another method, finite difference. So this is another approach, right? Up to this point, we've been working with the Euler method and the velocity relay method, and we've been discretizing time and looking at results. We've also been looking at some interesting physics. We're looking at physics involved with gravity between particles. We've been looking at with electrostatics, so the charges of electrons. We've been looking at also the Lennard-Jones potential as a way to model what happens between atoms. So we're going to attempt to bridge the gap from individual particles interacting with each other to solids today. Okay, so like millimeter scale and above type systems. And we'll talk about the boundary conditions that we use with the finite difference method that are relevant to heat transfer. So let's start off by looking at what we kind of might think of as being a bunch of particles, but we're going to think of them more in terms of packets of heat. Okay, so we're going to kind of discuss, wouldn't it be nice if we could use all we've discussed with particle dynamics to model how heat flows through solids? That would be nice, but of course, that may not be the most efficient way to do it. So, we have difficulties scaling the particles to the millimeter scale and beyond because what are the dimensions we've been talking about? We've been talking about nanometers, right? For these electrons that are interacting with each other, we've been talking about very small atoms as well. Bigger than the electrons, of course, but still very small. And so if you were to try to, I philosophically like, well, if we could just, we have all of that happening in these small little chips on the nanoscale as well, right? We're just getting chips that are bigger and bigger, and right, and then like, would you just have a chip that kind of simulates all the electrons and all the interactions and the molecules in the chip itself, right? Like the chip is actually that big. And then you're like, well, I should just do the analog experiment, right? If I've got a block of material that I'm trying to simulate, sometimes it just makes sense to build that block and try it out. Okay. But you can imagine as you're trying to keep track of all these different particles, like we discussed with the base pair approach, or we're trying to keep track of all these pairs and how they interact with each other. That can get very tedious very quickly. The physics might be a little bit more complicated as well. So, we've primarily been focusing on how these particles will interact with each other in terms of their motion. And now we're going to be talking about things like heat. And yeah, they're mechanical representations of the vibratory nature of the particles. Nonetheless, we had to make a jump, right? And there's a whole field of statistical mechanics. Okay? make that jump from, okay, what's happening at the molecular level, and let's take some averages, take some distributions, and then we can think about what's happening with thermodynamics. But the physics can get complicated. So there could be a simpler approach when you think about how heat transfers, how heat, and primarily conduction we're talking about, travels through materials. The other issue is that we might have difficulties measuring the parameters that we were using with the molecular dynamics simulations that we discussed last time. So epsilon was kind of the depth of that well, right, in the Leonard Jones potential, and sigma was related to the intermolecular distance. Those things might be difficult to figure out and to fit to a system that does model heat flowing through it. So it opens up our discussion and our treatment of new opportunities to be able to get useful engineering results without billions and billions of particles. And this new approach is going to now not only discretize time, but also discretize geometry. So we start to have some interesting accounting, right? Before we just had to account, well, we were accounting, we had containers, we had positions and things. Now we're going to have to up our game in terms of what we were accounting for. And we had to keep track of a whole grid of nodes, essentially, as we discretize our systems into different elements or voxels. So we're moving from this idea of having particles with discretized time to now having discretized geometries that would involve lines, plates, bodies, grids, and meshes in space. And MATLAB is amazing at doing some of these representations, extending these representations in terms of matrices. Okay. But people have realized there is a lot of money to be made in creating simulation tools that are a little more user-friendly than manipulating matrices with a script all the time, right? So that's where you get these big companies like ANSYS and Console, and Dassault, and all, there are a whole host of commercial companies, and then there are a whole host of open source solutions out there as well. Of course, none is really as user-friendly as what is available commercially, and so you'll get to experience with that. So yeah, any questions on the motivation? Why we have to move? Why we can't spend the rest of this class focusing on particle dynamics? You could take a molecular dynamics class, and that's what they'll do the whole time. They'll focus on many of these particles in kind of nanometer scale systems. That's not the focus of this class. We're talking millimeter. Any thoughts in terms of the motivation that we want to get across here? Yes. Yes.
Well, this scale of stuff is useful for macroscopic engineering structures.
Right, that's exactly right. That's where we're going. Okay? So some people would argue that we should have just jumped right into that. Okay? And I think we can thank Professor Singer for many things in this course. One of the ones that is particular is his insistence when he formed the course as we're experiencing it. There's some tweaks that we start from the ground up. Okay? So we're starting today. We're going to kind of bridge that, and we won't. How do you say it? We're not going to really look too far back. Most of what we're going to be doing is going to be with discretized space. Good points. Good point. All right, so one way, so now we're still going back to the particles, but one way to think of a particle and its motion is how far might it travel in a given amount of time, okay? Or in whatever the time frame that is, some characteristic time that is of use during your simulation. And so one way to describe this is what's called a mean free path. And this mean free path doesn't mean that like the particle is just going to move to this other location, that's the distance. It doesn't interact with anything else. No, it means, hey, given all the collisions, all the other particles that might be in the system, and all these interactions, this is how much essentially you would expect in a given amount of time your particle to wiggle to a new location, right? And it could be some kind of radial distance, like it's going to move somehow, in this ballpark. And you can think that, oh, if I got all these particles going around, then like things can kind of like shift or they can glide. But the particles, if you were to zoom out a little bit, a lot of these particles are essentially going to stay just in their neighborhood, right? You can think, these are the particles in my neighborhood. And just, I'm going to stay in this neighborhood, and I'm going to interact with my neighbors, and they're going to interact with their neighbors, and it's going to be some type of macro scale behavior that we get out of this. And so this statistical average length could also be something you could consider as being the length between collisions. Now, thermal conduction. All right, lots of words. I'm sorry. Okay. Thermal conduction is interesting in terms of often. Okay, well, when you think of thermal conduction, so you've taken thermodynamics. You should all be in fluid mechanics. Aerospace people, heat transfer is not a requirement here, but you're excited about that?
I took it.
You took it even though? Okay, great. Well, what is your understanding of thermal conduction based on what you've studied, based on your experience in the kitchen? I mean, what is thermal conduction to you? Yes. Sure. Right. Okay. So that's kind of a general. Yeah, that's a good way to look at heat transfer. Typically, right? You think about how heat moves, and in particular with conduction, what are we looking at? Yes. Okay, right. So yeah. Okay, so you could think of objects that are in contact with each other. Yeah. Okay. And sometimes you can think, oh, there's some contact resistance between them, like the heat, the conduction, the interface is not really perfect, and so you have some electrical. There you go. The analogies are going to be coming up, right? You have some thermal resistance there, right? Okay. What else? Yes. So there you go.
The conduction, like how the K constant, or
Yep.
is dependent on like how much electrons in the material are able to flow. It's also dependent on like the mean free path.
Yeah.
Forget exactly.
Yeah. Okay. Yeah. So you've got these, like we were talking about, all this vibration of these particles going on in a stationary object, right? And this is a solid, typically, when we're talking about conduction. And you have, you're gonna have liquids as well, but for today's purposes, we're thinking mostly of things that are stationary. So that means that they're going to be solid. Okay. You can think of the insulation of the walls in your house or your home, whatever it might look like. Okay. And you have this gradient where you have temperature, whatever it might be, 0 degrees Celsius on the inside, 17, 18 degrees Celsius on the, what did I say? 0 degrees Celsius on the outside, right? We're in winter right now, and 17 or 18 or 19 degrees Celsius on the inside. And that means there's a gradient there. And if there's a gradient, if there's a change in the temperatures, right, there's actually there's flow of heat, right? And obviously you're kind of losing heat to the outside, right? And then in the summer, we're trying to keep ourselves a little bit cool in New Jersey, and so maybe you're up at like 30 degrees Celsius on the outside. Okay, that's pretty hot, and you want to keep it down lower, so we got to pump the heat out somehow. Okay, but that's another way to think of the heat convection. When you think of, like, if for those of you who have taken some heat transfer, what is kind of the classic example that people use for heat conduction problems? Yes. Okay, the wall, right? Yeah. Okay, yes, they use walls, right? And we describe these with resistances and things. What else? Like the first one, you're sitting there with Professor Diaz or Professor Say, and they're like, all right, what is the first thing you do in conduction? Yeah. Equation. Okay, yes, you got an equation. Okay, let's think physical for a minute.
Oh,
Yeah.
I thought you were asking for equation.
No, okay, well, we're going to go into some equations in a minute, okay? Yeah?
Conduction between two plates.
Yeah, so I would even say before that, bar, right? Like you got a bar, and it has some initial temperature, right? And you have like some temperature on one side, and you're looking at what's going to happen to the temperature inside the bar, right? Or you're looking at the Q, right? The heat flux to the bar. Maybe this sounds somewhat familiar, okay? Because that's what we're going to do today, right? So let's talk about heat and packets of heat. So this kind of looks like a particle, but it's not really supposed to be a particle. Okay, this is some type of entity that is a particle, I guess, but it's like a packet of heat. And yeah, okay, so you wanted to talk about boundaries and interfaces, so let's talk about an interface. Okay? But this interface could be like kind of inside something, all right? But here's the boundary. And this could be a boundary that's like, I got this bar of aluminum or I got this bar of steel, right? And we're mechanical and aerospace engineers here. If you're going to think about how heat spreads through steel, generally speaking, or versus aluminum, which one has kind of this higher thermal diffusivity with it as it goes through? Yes? Yeah. And why is that a problem industrially speaking? Or it is a problem industrially speaking, yes. Yeah, have you done some welding? All right, yeah, so you know that steel is amazing because it actually doesn't wick the heat away very quickly, which allows you to use some type of torch to be able to get a high concentration of temperature in a localized area so you can melt your flux plus some other metal into that little crevice, right? So steel is good at this. Aluminum, it wicks heat like mad, all right? And so they have to come to that, and it's not impossible, but you have to come up with some creative ways. So friction stir welding, for example, has been one of these approaches to try to weld different pieces of material together. All right, that was a little bit of an aside. So we have these packets of heat, and they can go some length. We'll call it L on either side of the boundary. And so they're kind of bouncing around here. Now, what is the flux across this boundary? Well, what do you remember? Yes, go ahead. Right, and it's over some area, right? So, like, technically, right, when we think of the flux, we're thinking of something over an area. Yeah. So we're going to think of this change in energy with respect to time. So that's dE dt. What would units of dE dt be? Someone else. Yes.
Joules per second.
Which are?
Watts.
Yes. some type of area. Okay, so we got some, so typical units here would be watts per area squared, or watts per meter squared. Okay, like that. All right, and that is, I mean, there's sometimes some confusion. Is it a big Q? Is it a little q? We're going to say it's the little q here. And we're going to say that, yeah, it can be thought of in terms of having some type of direction, right? Usually when you think of flux, and you're going back to your multivariable calculus days, you're like, don't do this. I'm like, yeah, don't do it either. All right, so, but you remember there's like a normal, right? So any surface, a normal vector at any location along the surface, right? And you're thinking, okay, is my flux, am I going in against that normal, or am I coming out with that normal, right? So we have this flux. So what does that have to do with the diagram above? Well, you can think of there being, okay, some direction associated with this vector, some density of these packets of heat. All right, so you could have more of these or less of these, but you have some kind of density of these packets. We have the speed at which they might be moving, and we have the energy associated with these packets of heat. All right, so the density we can think of, and this is just kind of some aerial, like 2D problem here. Okay, so we're looking down on the system. We have some number of packets per like area. We have speed, which we can think of as length per time. And then energy we can think of as this interesting limit, okay, that says, okay, if I go a little bit above, all right, I have some energy. If I go a little bit below, I have some energy, and I'm going to divide by the 2L. All right, so it's kind of like I've got now all the energy of the packets in this area. Okay, and there's some density associated with it. We had a number of packets in area, but this is going to be kind of our area function. And you see what's going on, though? We're going to shrink that down because we're interested in what's happening on that boundary. Okay, so at that interface, we shrink it down so we make L smaller and smaller and smaller. These slides are available, so we're going pretty fast today. There's actually quite a lot of material that I hope I'll get through it. Okay, so I know it's really nice if I'm sympathetic and write everything out, but I'm not. I'll probably be more sympathetic in mechanics and materials in the future. But today we're going through quite a bit of stuff. So don't fret. Just we're going to use the think method here, okay? So what does this look like? This limit. What does it remind you of? If something goes to 0 and I have a difference? Yes.
Derivative.
It looks like a derivative, right? Okay, so we take that, and that is going to be some change in energy, okay, over dz, or so the dE dz. And yeah, don't worry too much about the signs, okay? But they're there. And then we can use the chain rule, and we can say, hey, I'm going to take this derivative of the energy with respect to time, but temperature, and I'll multiply by some change in temperature over dz. Now, this delta, this dt over dz, you might start to think, oh, that kind of has a physical meaning to me. That's like some change in temperature over some length, right? So we were talking about the gradient you can have in a wall, insulation right inside, outside, right? So that is, you're already kind of seeing, it's coming in. It's coming into play here. Okay. So if we break down this thing, we have some energy per mass per temperature, and we have some temperature per length. When we put all of this together, okay, like all these things, we should get the balance of the units. Locally, in this part, this right here this quantity here, this energy per mass per temperature. Anyone dealt with that before? It has a little symbol. It has a name. Right? So this is, you think, all right, what's your favorite material to absorb heat, to store heat in? I'll think of liquid here too, yes. Water is a great one, right? Water is an amazing heat sink. So water has a high heat capacity. And so now we're talking about, okay, the heat capacity. Remember back from your chemistry days probably, right? It's like, oh yeah, MC delta T is equal to what? Yeah, some type of energy, right? Right? Some type of enthalpy, some type of change for MC delta T, or MC delta T, right, was equal to the energy you're putting into the system. That's going to be the thermal energy. That's going to be how much the thing rises in temperature. So we got this interesting balance as we put everything together, right? We've got a temperature gradient now. We've got some measurement for how much energy it requires to raise the temperature of the material itself. That's with the heat capacity. Okay, we have some direction. We have some speed at which all this thing is happening. Okay, and so we now get closer. All right, to also naming another quantity. Someone mentioned the K. What do we use K? What do we use the K to do? What is the English word for K? I mean, yes, English K, lowercase k. But what does that K represent? Okay, this is lowercase k. Sure, the capital K is Kelvin. This is something else. Yes. Yeah. So this is the thermal conductivity. Okay. So this is now giving us some idea of how does temperature then, well, they're all related. You have heat capacity, you have temperature, right? But this is giving you an idea of how quickly can these particles, okay, flow through a system, flow through a solid, okay? And it takes into account the heat capacity as well here. So then, in the end, this equation becomes something that's kind of simple. You have a K, you have a dt, dz, and you have a negative sign, and you have a direction. Okay? So this is what we write for heat flux. And we'll have another version. This is what you call Fourier's law, essentially. And this is just in 1D. So do you see what we kind of did here? We kind of roughly said, look, you've got these packets which are kind of like particles. They can kind of go some characteristic length. And then we said, boom, we're going to just have this very simple equation, and we're no longer talking about particles. This is kind of important and profound. So I don't have to keep track of all these particles. I just have to keep track of a first order differential equation. And then there will be the partial differential form of it as well. Okay? So we have heat flux across the boundary. This is a vector quantity. In 1D, it looks like this, as is Fourier's law. Okay? And the K is, you can think of it as some power per length per temperature. And we can then also think of the dt dz in terms of that's some type of Kelvin, all right, some type of temperature per length. Okay, some people would be upset that I even put these units in, right? They're just like, just think of it in terms of the general entities. All right, but whatever. You can see the K's cancel out, and we get, once again, power per area. That is the heat flux. How do you deliver heat flux? What's your preferred mechanism? What are your preferred mechanisms for delivering heat flux? And you could say, oh, I'm just going to talk about the 3 forms of heat transfer. I'd be okay with that if you explain it. Right? Or you could talk about it as some other thing. But what are your favorite forms of heat flux? Yes? I don't know if okay, so a radiator. Okay, what do you mean by that? So like the one that like is distributed is providing heat to your room. That's on the corner on the baseboards. That kind of. Okay, yeah, sure. So you got some heat flux into the room. Yes, good. Okay, others? Not what I was thinking. I mean, there are lots of different ways. How else? Yes? You raising your hand? Yes. Yeah, physical contact, right? So like that would be conduction, right? And that's where you all were going initially. Like, I just want those 2 plates. Yeah, you got a hot plate and a cold plate, right? Heat flux. You also have heat flux, as we're describing here, within a material, okay, itself. Right? If I think of this element of the material and this element of the material, I can think of, oh, how's the heat transferring between the 2? So there can also be that local flux. We talk about welding, right? So we can have a torch. Anyone ever use like a torch to destroy their beads? I tried it for the first time. It's kind of fun. But this past summer it was really dry, so or past fall. Well, the weeds weren't a problem. I got to them before. It's kind of fun. But really, your cooling weeds. Yeah, I don't know. It's not necessarily the best. It's not the only way to remove weeds. Right? There are mechanical ways to do it, but it's kind of fun to see what's going on. Okay, what are other ways of delivering flux? Yes?
Like an oven, like convection.
Yeah, so you have convection, that's another form of heat transfer, right? And that's like the radiator kind of thing, right? You got some ability to like for example, the radiator, right? Like if you're thinking, okay, I'm putting hot water into it and then it's putting heat into the room, you could also kind of think of it the other way. I've got this convective flow that's taking heat away from the radiator. Okay, and so that's another way to think of flux. Air is getting that. And then we have radiation, which we'll talk about a little bit. All right, we all appreciate the sun and what it does for us. So there are multiple ways to get heat flux into your system. Okay, in 3D, this is what Fourier's law looks like. And what is that quantity? That is the gradient, right? So that is just the gradient of temperature. It's not that scary if you think of it as three versions of the one. Okay, so what we're going to need to do, you're like, why are we doing all this work? Or maybe you're like, oh, this is really boring. That's fine. Okay. We have to take this equation and we have to change it. We have to discretize it, right? We said we have to chop space up into different chunks. And we can discretize it to be able to put it into the computer. Okay? So we can also think of heat flux into and out of a region. So we just talked about, the torch, the radiator, the radiation, convection, whatever it might be. But if I go back to that solid we also talked about, right? And I think, okay, here is a chunk of material. It has some cross-sectional area A, and it has some length dx. We can think I've got some Q coming into this left side, and I have some Q coming out on the right side. And what have we done here? We've done something kind of important and kind of new. We're saying, there is going to be some Q at x plus dx. Right? So we're starting to say, oh yeah, maybe I can start to think of my system as a combination of a bunch of dx's. And to this chunk of material, we can assign a temperature. So, the change in energy in time of this chunk is going to be dependent on some type of heat flux and potentially some type of mechanical working flux. Okay? We're getting into some of your thermodynamics, right? You should like this. You like this? This you like. Okay, good. And what happens to the work? Well, we don't care about it. We're caring about the heat. And so once again, okay, we have something that looks like Fourier's law. If you want to think of, okay, so it kind of starts to look like Fourier's law, all right? But what we're really talking about is what's happening on the left side. Okay, this is some type of volume, AdX, right? That's the volume of the chunk. C is a specific heat capacity. Remember that? And that was like, oh, that's like, it's not just like the big C for the whole system, right? That's going to be giving us some idea of what it is per unit volume. And then we have the ddt, and we have density. Okay, so we put all those things together, and that's the left side. On the right side, which is the dq dt, we bring in Fourier's law. Okay. And so what you're seeing there, right, is this, oh, this is a qx coming in from the left, and this is a q of x plus dx on the right, and it's working over some cross-sectional area. Remember that this q has units of watts per area squared. So now, okay, what we've got is a nice equation. And we can think of the change, it's the same, just copied, right? What do you think we're going to do? Well, if I'm interested in ddt, when I say dtt, I say I'm talking the change in temperature with respect to time, right? Maybe I just put the rho over c, okay, on the other side. Maybe I also begin to write out what Fourier's law really is, and I have these other dt's here, okay, like this. See this? This is the gradient, and this is a ddt with respect to time, and this is a dt with respect to space. This is also kind of a profound moment because I think it highlights that, okay, I've been discretizing time in my previous simulations, and now I'm seeing derivatives not only with respect to time, but I'm seeing derivatives with respect to space. Okay. So we can take this expression right here and look at that. Remember, we had an expression that was out there similarly before, right? We had the limit as L went to 0, and it was like the difference of two quantities. But this is like the difference of two derivatives. So this can simplify or be written as the derivative of this quantity, which means it's the second derivative of the temperature with respect to x. Yes, question? Okay. So, now we went from Fourier's law to the heat equation, okay, in 1D. So we've got some, and we moved the rho c over here, like we're talking about, and we have written it out in this form. So this is with respect to time. This is with respect to space. All right. So this is very nice, and we have a pretty good idea of how we can approach discretization of time, right? We can kind of march through, maybe with Euler, right, method or something of that nature to get us through that part. What do we do with the space? What do we do with that second derivative? How do we put that into the computer? Wow, okay, when have you done this?
For CFD.
Oh, okay. Were you taking CFD? Wait, you're taking?
No.
No?
No.
No? Wait, no, what?
Not the class.
Oh, okay, you've just done it for kicks.
No.
No.
You're into a research.
Oh, for research. Okay, yeah, okay. So not for kicks, for research. Research can be for kicks, though, right? Yeah, so what you said, we're going to do some finite difference, and that's the name of the method that we're using today. And we're going to turn the clock back to something that you learned a long time ago. Okay, and this is the 3D version, okay? Which is important, of course. And you see now we have this nice partial differential equation, right? Those are partials, and yeah, that's when whenever I see partials, my inclination, because I come more from the dynamics and controls background slightly, manufacturing, as much as possible, I want to try to get an ODE as soon as I don't want to stay in the PDE world. All right, I'm like, as much as possible, give me some lump parameters, please, so I can just go to my ODE 23 or my ODE 45 and solve it. Okay, but no, we can't do that today. Right? We have to face this adversity together. Speaking of which, oh yeah, we're good. We're good on time, I think. All right. So so what do we do to handle this? Okay, and yes, there's a quantity. What do we do? We're going to. We can maybe come back to this a little bit. We're going to go to. Actually, I want to skip because I was just there. We'll come back to that, but we're going to go to the math. All right? We're going to go back to the days of calculus where we said, if you're stuck and you have to take a derivative, you can use, or if you want to use derivatives, better said, to solve for a particular value at a particular space, you can use the Taylor series approximation. Okay, so here we are. This is saying that, okay, if you have some function that you can differentiate that's f of x, okay, we can think of it as being, and you know what the value is kind of next to it, right? You can think of, all right, of taking that value plus the first derivative of it plus some version of the second derivative of it with some this 2 factorial and this x minus a squared term, and then you can keep going, right, infinitely. And you can get a really good approximation if you use a lot of terms of the Taylor series expansion. Well, we're not going to go too many deep, all right, in terms of the number of terms of the Taylor series expansion we're going to keep. But maybe we can use this as a method to solve for that second derivative that we had. Right? We saw that we had the second derivative with respect to space. If we took one, just was in 1D, that was the derivative of the temperature with respect to x. Second derivative of temperature with respect to x. So there are approximations that can be done here, and we can go forward, for example. All right, and this might look a little bit similar. We've done it in time where we said, hey, if I want t of I plus 1, or if I want the velocity of I plus 1, right, I have to do something explicitly at my current time step to figure out what's going to happen in my next time step. And so this would be kind of like the forward approach, right? So if I want to know what the temperature is, not necessarily in the next step in time, but to know what it is at my next space particle or space element, right? The xi plus 1. I can do it by using what I know for temperature at this location and what I know about the gradient, okay, the first derivative, and what I know about the second derivative, as you see here. So we're going to, and these are just using second order, right? So we're taking the second derivative. And we can think of, all right, well, this dtx right here, that I can think of as a difference. And here we are, folks. This is your dtxi. That is a finite difference. And this is a finite difference in the x. So this is the space, the delta x is the distance between this spot and this spot, for example, in my 1D bar. Okay? And the temperature, all right, in that next spot and the temperature in my current spot, okay, is this difference here. So you see where we're going? So this is now a finite difference. This is a first order finite difference. Now, what do we have? We have a second derivative, right? Okay. So before we get to the second derivative, we can also go backward, okay, like this. And we're just going to kind of burn through this, all right? So we can go backward. So if you wanted to know what's going on in the temperature of the before, okay, you can do it this way and go backward. So like, okay, so if I'm, this is my x of I, this is my x of I plus 1, this is my x of x I minus 1, x of I minus 1, right? So you can kind of see, I can go forward. Any of you good dancers? I'm a horrible dancer, right? But we're kind of dancing now, all right? Forward, backward, like that's like merengue or something. All right, and then we can also do central, a centered difference, and that's what I think you were saying. That's your preferred approach. Okay, so we've talked about the forward. That's just rewriting. Okay, talked about the backward. That's just rewriting. Okay. What does centered look like? Well, centered kind of looks like putting them together. So now, see, if you do this plus this, and you put these plus these, you can actually kind of figure out what's happening at your location. So now, if I'm in this middle, I can figure out what's going on here based on what's going on here and what's going on here. Any questions on how this is working at this point? Any thoughts, insights you'd like to share? We've kind of gone backwards, right? It's like, hey, we did all this calculus so that we could take the limit as the distance goes to 0 to make derivatives, and then we know what the derivative of a polynomial is, so then we can just do that thing real nice and easy and come up with analytical answers. Now we're going backwards, essentially. We're saying, hey, look, there are a bunch of derivatives in your equations, and we're going to go back to thinking about what's going on, between the neighbors, and how you calculate those differences. And you're seeing that we're going to have to keep track of all this. Okay. So, this is a nice little plot from the internet, kind of showing that you have this backward difference way of looking at things, you have the central difference way of looking at it, and a forward difference. So, the nice notes to keep track of in these problems, but which ones do you think are the nice ones? Which ones are the ones that will keep you up at night? The ones in the middle of the bar, or the ones at the ends of the bar?
Yes.
The ends are going to keep you up at night. All right, why is that? Yeah, you got a boundary, right? So we're saying, hey, everything is like insulative. Nothing's going on here at this top boundary. Nothing, right? But like here and here, you got flux, you got temperature that you might be setting, you got all kinds of issues at the ends. And so we gotta go in and in the middle, you can just like, oh, everything's awesome. I can do my center difference. I can do like, and we're gonna do second derivative in a minute, right? But you can just like do everything, and you're like just marching along, and then boom, you get to the end, and you're like, all collapsed. What do I do? I mean, I got to think about how the particle next to me is interacting with it, but I also got to think of what's going on in the outside world. So the boundaries end up being tricky, and we'll see that in a few minutes. Okay? You can also begin to plot profiles, okay, of temperature. And you can think of, okay, yes, this is that one snapshot in time, but it's like a video, right? It's going to potentially change. You're going to see spreading out of this heat, or of these temperature profiles, and we'll show that in a minute too. Now, how do we handle the second derivative? Well, we can use the Taylor series approximation again, or expansion. We can add forward and backward Taylor series, including second order terms. And I'm not going to go through this right now, but this is what they kind of look like. All right, so you can say, oh, I'm going to take the second order term, and I'm going to add these other terms, okay? Or like the centered, right? Remember what we did? We took the backward and the forward, and we added them together. So we can do that, and this is what you get to see. You see that there is this interesting behavior where the second derivative is going to be dependent on if it's center difference, okay, it's going to be dependent on what's happening in the forward. It's going to be dependent on what's happening at that location. It's going to be dependent on what's happening behind it as well, okay, that second derivative. And then if you see, oh, I can look at a second order forward, it's dependent on two, not one, but two in front, what's happening, one in front, and what's happening at my location. Okay, so this can also be somewhat of a useful approach when you get to the boundaries, although we're not going to necessarily handle it this way in this class. And then you can think of the backward as being dependent on what's going on here, what's going on one behind, and what's also going on two behind. So this is again, we're taking these derivatives and we're breaking them into finite differences. Right? All these things can be kept track of in a good accounting scheme. Okay. And so this is what this looks like in the nomenclature that we're using. Okay, now let's go back. I skipped a couple things. We did the math. I thought you liked the math because that's the direction we had gone. There is kind of an important physical quantity to keep in mind. And that is what's called thermal diffusivity. And it's this ratio of the conductance, or the conductivity, divided by the density and divided by the viscosity. So a material that can really see temperature or heat whip through it really fast would be one that, hey, it's not going to absorb, it doesn't take much, it could have like a low density and it could have a low specific heat, so it doesn't really have to take that much energy to get it to change its temperature. So it could have, that would be a low rho, a low C, and it would have a high K, a high lowercase k, high conductivity that allows it to whip through. So what you often will see when you do these simulations is that you just have an alpha here, and so you even get, it gets simpler, so you get a dt is equal to alpha times the gradient, the Laplacian, okay, the second, the delta squared, if you want, of t, okay? This Laplacian operator on there. So thermal diffusivity is an important quantity, and you can look at different tables, and you can get an idea of some materials that that have high thermal diffusivity and some that do not. So for example, here we see that steel has, at least in comparison to some of these other materials, has a lower thermal diffusivity. And if you look at, remember we were talking about that in comparison to aluminum, right? So aluminum is like a factor of 10 higher in its thermal diffusivity than steel is. So that's what we're talking about welding and how the heat whips through that. Okay. And then you can also look at thermal conductivities as well. Okay. So air has a pretty low thermal conductivity. It's a nice insulator. And copper does not have a low thermal conductivity, right? Copper definitely allows us to go through it pretty quickly in terms of its thermal conductivity. Of course, its density is a little bit higher than a lot of the other materials that we might be dealing with. Okay. So, but you can still see that it balances. Copper ends up having a higher thermal diffusivity than aluminum. These can also be temperature dependent, so the thermal diffusivity and the thermal conductivity, they can change as a function of temperature as well. Okay, let's go ahead and let's just go through. Let's see. Let me show you some examples. All right, because might be a little bit bored here. Okay. So this right here is a 1D problem. Okay, and it's discretized into 11 points. You see that? And we've assigned temperature to those 11 points. What does the temperature look like in this bar with these 11 points? What does the profile look like? The way it's written out here. Just look at the numbers. Sure, go ahead.
It's hotter on the right side.
Right. If we're saying that column 11 is on the right side, right, it's at 310 Kelvin. I can tell you what the units were, right? And on the left side is 300. Okay, so if we plot this out and see the T final right now is just 0. So this is just showing the initial conditions. So I have, where did I prescribe it? I prescribed that, or Raman or Professor Singer, in this case, have prescribed this linear profile on temperature. Now, knowing what, just having, how do you say, some intuition, if you prescribe this thermal profile, what is going to happen to the temperature in this bar as time progresses? Yes.
It's gonna kind of like equalize and return to steady state with like every section being at one temperature.
And what would that temperature be?
Maybe the average.
Yeah. All right. That's exactly right. So in this situation, now the boundary conditions, we haven't talked about what we're doing at the boundaries yet. Okay. This is going to be, it actually has an interesting property which we'll get into algorithmically in a little bit. But yeah, this thing, right? We talked about thermal diffusivity. This thing is essentially going to diffuse or blur. All right. And we're going to see this thing kind of gradually get so that the average temperature across it is 305 Kelvin. So let's give it some time. And you see we've discretized dt, so this would be 10 time steps, okay? And you can kind of see, oh, something interesting is happening at the edges, right? The edges are actually kind of this is actually looping around algorithmically. All right, so what's happening is the temperature on the right side actually ends up being the temperature on the left side. They're communicating with each other. That's a periodic boundary condition. Remember that? And you see what's happening. These nodes, as time progresses, they're the colder, a node that's colder than it on one side is going to bring temperature down. A node that's hotter on one side is going to bring the temperature up. Right? This is using the heat equation, but it's discretized. Okay, so we have our second differences that we're keeping track of here. If we go a little bit longer, let's go 10 times longer. Okay, what are we going to see? Okay, and you can see the numbers down here, they're changing. Okay, you can see that after 10 seconds, for this particular system, it kind of equilibrates. Do you see that? This is how we're creating videos, essentially, that are showing us how the temperature profile changes as a function of time. Now, if you have an initial profile that looks something like this, somehow I magically am able to get a temperature distribution that looks like this. What is that? That's like, some sine waves. 4 sine waves. What's going to happen? Yes?
It's just going to equalize the same way to 300, but it's just going to be slightly, like it's just going to be thinner sine.
Yeah, that's good. Now, what is the derivative of let's say, a sine omega t? Yes.
A omega cosine.
Right. Okay. And the second derivative would be a or negative a omega squared sine omega t, right? So, what you can kind of begin to see is that there's this omega term, like omega squared, as you take derivatives of it. That omega is kind of related to the slope. It is related to the slope, right? So if you have a lot of sine waves, or if you have sharp gradients in your material, that will lead to fast diffusion. Why? Because the heat flux, right, is going to be dt dx. Okay? Or partial t with respect to x. So one to be a problem. Okay? So that heat flux is actually very high when you have high frequency distribution of temperatures. So let's run this, and as I think you've expected, right? You see it very quickly. That was less than the other example we had. Okay? It wants to flatten out because those derivatives are very large. That's now if I have a sine wave that's has a longer wavelength, right? Then the derivative is going to be smaller, so it's going to take more time to smooth that. And then let's now start talking about boundary conditions. Okay. So this Professor Singer has a very clever way of implementing these finite differences, and he uses what's called circ shift, which actually takes all the elements or all the temperatures and it shifts them one over, and then he can subtract them from each other, and that becomes the first difference. And then he can do that a couple of times, and then he has all the quantities he needs to do first and second differences. It's quite clever. Okay? And I talked to him, I was like, hey, I haven't really seen this in a textbook before. It's like, oh, yeah, I just thought this is the way to do it. Okay, all right, dude. Okay. I don't know, he probably got it from a textbook somewhere, but that's how he implements it. Okay, and so this circ shift, it essentially implements the periodic boundary conditions as well, because it actually cycles all the way through, so the left and the right, like we've discussed before. Now, what happens? And these are perturbations, all right, high frequency, we got to talk about boundary conditions. I like this boundary condition, not just because it's French, Dirichlet, all right, but because this one, if you go back and you look at this boundary condition, this one, if you look at it, I got to go fast. This one is just prescribing temperature at the boundary. Okay, so it's like, hey, temperature at 0, which would be the left side on this in this case, is going to be fixed at a temperature. That's very nice, because why? Because when I have my Dirichlet, when I have my finite difference, surface shift, everything going on, and I've got my second derivatives, my second finite differences, all I gotta do is say, nope, at that location on the left, this is the temperature. So whatever value you end up circulating into there, get rid of it, it's now this temperature. Okay? And then it can calculate everything else. Same thing on the right side. So it's at this temperature, right? So Dirichlet is kind of simple. Yes?
Is that not realistic?
That's very realistic in many cases. Yeah. I mean, well, actually, okay. It's realistic if you have a large thermal mass. Okay. So like if you have a huge chunk, like the ocean, right? It could be at a temperature, right? And I drop a hot metal rod into that ocean, okay? And I've got enough circulation, right, going around that I can just say, okay, yeah, this is a bath where the temperature is the same. Okay? It's not that bad of a approximation.
Looking at this picture, let's say you want to measure, like let's say it was steel rod that you heated into orbit or somewhere and let it air cool.
Correct. No, you're going to have to use convection, and that's going to communicate to the device, to the rod, to the Neumann boundary condition. Okay. What is the Neumann boundary condition? The Neumann boundary condition, and I thought I was funny, but maybe not. There's a Seinfeld episode where they're like, "Hello, Newman. Hello, Newman." So your post-lab exercise, you can YouTube it or whatever. Hello, Newman. It's not Neumann, but it's called Hello Neumann. Okay, that's the post-lab exercise. That's the joke. Anyway, so if you have the Neumann boundary condition, this is where you essentially you say I'm prescribing flux. Okay. Now, when you brought up an interesting point. When you have convection happening, convection is dependent on the differences in the temperatures, and we introduced what's called an H parameter, okay, a convective thermal coefficient. So there's a difference in the temperature between the surrounding media and the bar itself, and it could be on all sides if you want, right? And then there's some coefficient essentially that relates that temperature difference to the heat flux. And that is a more realistic expression for what you're trying to have with convection. Okay. So those are kind of the two big ones. Plus, there's also going to be an insulating boundary condition as well. Okay, but this one is just a heat flux that's coming into the bar or out of the bar. How are these implemented? Well, Dirichlet, like we were saying, it's implemented just by prescribing the temperature at the left and the right. Okay, so that's really nice, simple. And you can do it in 2D as well. Okay, so what happens in 2D, all right, so here's now your first 2D mesh. First 2D grid. You see each of those points is a value to us. When you get to the corners and the left and the top and the right, as you're doing your for loop, you have to prescribe the temperature at those locations. That's what we do for Dirichlet. Okay, does everyone see this? This is kind of important. It's kind of a pain. Alright? So this is how it works. And you'll get to heat a turkey. Everyone excited about turkey? Alright? How long do you typically keep a turkey in the oven? Well, after this exercise, you'll have some pretty good ideas. So that's the post lab. That's one of the things. All right. So with Neumann, all right, you have to know what the heat flux is, and this is more complicated, and the accounting is kind of a pain. All right. I have no lie. Okay. So you remember though that one way to think of Fourier's law is to think of, all right, I've got this chunk of material and this chunk of material. Now, essentially, what we're saying is, well, you've got like this not chunk of material, but you've got a boundary on the outside that you can apply this heat flux. So instead of putting a dt dx in that on the right or the left side, what you do is you put a heat flux. Okay, and there's got to be some scaling by the appropriate kit as well. But that's how we treat this. It's not that complicated, really. It's just recognizing that we've taken Fourier's law and we're now assigning a quantity to it. Okay, and so you can see how this is implemented, and you have to keep track again of the corners, and you have to keep track of the sides, and it's a pain. It's a pain. Okay, it's an absolute pain. This kept me up a lot when I implemented it. All right, this was not. So hopefully. Hint, do not mess with much of the code here, okay? I mean, you've got to do all the coding, right? But there's going to be like a part where I say edit, stick to that spot, all right? Because you don't want to get into some of the inner workings, inner bowels of these for loops. I mean, you should understand them, but I'm not expecting you to mess with them, okay? All right, so, I just want to show you some turkey stuff. All right, because this is fun. So when you do the 2D problem, okay, you're going to specify the temperature of a turkey. That I'm going to say is like a square. So there, that's a frozen turkey. Now I put my nice boundary condition on the outside. And what I'm doing is I'm looking at how the inside of the turkey progresses, right? You take, hopefully, well, different people have different ways of doing their turkey business. All right, but you have, generally speaking, you have something that's very cold that you stick in the oven for hours. Right? And yet what you're trying to do is you're trying to get inside temperature for the core of that turkey to be safe enough for you to eat. And you don't want to dry it out. Okay? So the next time you cook a turkey, you know its mass, you can estimate it with this calculations to figure out how the profile is going to change over time. Okay, let's go ahead and we'll do the attendance.